650 light-years away, in the familiar outline of Orion, there's a star that is quietly counting down to its own destruction. One day, that star will tear itself apart. In just a few seconds, it will release more energy than our sun will produce in its entire 10 billion-year lifetime. A wall of radiation and stellar debris will race outward at thousands of kilometers per second. Anything close to it, any planets, moons, or dusty disks, would be hit with a blast so intense their atmospheres could be stripped, their surfaces melted, and their entire systems permanently reshaped. And here's the twist: it will look terrifying, but it won't be the end of us. Because this future supernova is not some distant, invisible event at the edge of the universe. On a clear winter night, you can walk outside, look up, and see the star itself with your own eyes. It's one of the brightest points in the night sky. It's the reddish star marking the shoulder of Orion. It's called Betelgeuse, our nearest red supergiant. Astronomers agree on one thing: Betelgeuse will explode. It's not a question of if, it's only a question of when. So how soon is soon? Are we talking hundreds of thousands of years? A few centuries? Could it happen while humans are still around to witness it? And if it did, would it be a harmless sky show, or something that could actually affect Earth? In this video, we're going to unpack what we've learned about Betelgeuse, and we're going to do it in a way that answers the big questions in order. First, what kind of star it really is, and why red supergiants behave so wildly. Then, how dangerous a nearby supernova really is, and why distance changes everything. Then we'll solve the mystery of its famous Great Dimming in 2019. After that, the evidence that Betelgeuse may have a hidden companion star. And finally, the strangest puzzle of all: why Betelgeuse appears to rotate so fast it almost seems to break physics, unless our telescopes are being fooled by the star's own boiling surface. By the end, you'll see why Betelgeuse has become one of the most closely watched stars in the sky, and why, even though it's definitely going to blow, we don't need to be afraid of it. Let's start with the basics. What are we actually looking at when we look at Betelgeuse? What Betelgeuse really is. If you've ever looked at Orion, you've almost certainly seen Betelgeuse already. Picture Orion, 3 bright stars in a straight line for the belt, 2 shoulders above and 2 knees below. Betelgeuse is the bright orange-red star forming one of those shoulders. Despite being about 650 light-years away, it ranks among the top 10 brightest stars in Earth's night sky. That alone tells you something important. It must be either unusually close, unusually powerful, or both. Its color is the first big clue. Most bright stars in Orion look white or blue-white. Betelgeuse looks redder, like a hot coal that's starting to cool. That means its visible surface is cooler than the sun, around 3,500 degrees Celsius, compared to about 5,500 for the sun. But cooler does not mean weaker, and it definitely doesn't mean small. Betelgeuse is a red supergiant. It began life as a star far more massive than the sun, likely around 15 to 20 times heavier. Massive stars burn through their fuel fast. As they age, their outer layers swell and puff outward, turning them into enormous, diffuse giants. If you could place Betelgeuse where the sun is, its outer surface would swallow Mercury, Venus, Earth, and Mars, and stretch close to, or even beyond, Jupiter's orbit. Its radius is roughly 800 to 1,000 times the sun. And yet, it has only about 10 to 20 times the sun's mass. The same amount of material is spread out over a volume millions of times larger. That makes its outer layers incredibly low density. The surface of Betelgeuse is more like a hot, glowing fog than anything solid. Gravity there is weak, and the star is constantly churning. Giant convection cells, bubbles of rising and sinking gas, move across it. Some of these cells are so large they can cover a huge fraction of the star's visible face. If you could hover near Betelgeuse and look closely, you wouldn't see a smooth, perfect ball. You'd see a massive, boiling sphere with bright patches, where hot gas rises, and darker patches where cooler gas sinks. Those patterns shift over months and years in a slow, restless dance. This is not a calm star. It's a turbulent giant in the late stages of its life. And late-stage massive stars have one thing in common: they do not end quietly. How dangerous are supernovae, really? When people hear nearby and supernova in the same sentence, it's natural to think instant extinction. These are among the most energetic single events in the universe. But powerful doesn't automatically mean dangerous for us, especially at hundreds of light years. Here's the simplest way to think about it. Supernova danger is mostly a distance problem. Astronomers detect supernovae in other galaxies all the time. In our Milky Way, they're rarer, maybe a couple per century on average. Some happen on the far side of the galaxy behind thick dust, so we miss them entirely. And Earth has almost certainly experienced nearby supernovae before, not as a story, but as physical evidence. We live inside a region called the local bubble, a cavity about 1,000 light-years across, filled with unusually thin, hot gas. The best explanation is that a chain of supernovae carved it out over the last 10 to 20 million years. And we have fingerprints of that. Geologists have found traces of radioactive isotopes like iron-60 in deep-sea sediments, tiny crumbs of material that don't form naturally on Earth in significant amounts, but can be produced in supernovae and then drift here through space. In other words, Earth has literally been dusted by nearby stellar explosions before. That doesn't mean they're harmless. It means distance decides the outcome. So how close is too close? Rather than memorizing a pile of numbers, it helps to think in 3 zones. In the danger zone, roughly within 10 light-years, a core collapse supernova could be catastrophic. The initial blast of high-energy radiation and the years-long flood of cosmic rays could seriously damage a planet's atmosphere and threaten surface life directly. In the caution zone, roughly out to 20 to 30 light-years, the biggest risk is the atmosphere. Ozone depletion could expose life to much more ultraviolet radiation from its own star for years, raising mutation rates and stressing ecosystems. Beyond that, you're mostly in the light show zone. At around 100 light-years, you might see measurable changes in the cosmic ray background and upper atmosphere chemistry, but it's unlikely to sterilize a planet. And at several hundred light-years, the direct danger drops dramatically. Betelgeuse is about 650 light-years away. That puts it far outside the zone where we'd expect serious biological danger. When it explodes, the flash will absolutely be detectable. Satellites will see it. Telescopes will go wild, but it will not strip Earth's atmosphere or boil our oceans. And we're not just sitting exposed, either. The sun constantly blows a stream of charged particles outward, inflating a protective bubble called the heliosphere. It doesn't block everything, but it helps reduce how much galactic radiation reaches us. Even the physical shock wave from the supernova, actual expanding debris, won't arrive for tens of thousands of years, and by then it will be so spread out and diluted that it will be more like a mild change in our space environment than a cosmic hammer blow. So from a safety perspective, Earth is fine. From a spectacle perspective, though, things get genuinely incredible. What we'd actually see. If Betelgeuse went supernova and we were around to see it, what would it look like? First, a strange detail. When the explosion happens, we won't know right away. The light takes about 650 years to reach us, so the event itself could have already happened centuries ago, and we simply haven't received the signal yet. But once that light does arrive, the change will be dramatic. Over hours to days, Betelgeuse would brighten enormously. It would go from a bright reddish point in Orion to an object rivaling, and possibly outshining, the full moon. It would still look like a point of light to the naked eye, not a disk, but it could become bright enough to cast clear shadows at night. For weeks, it would dominate the sky whenever Orion was up. Even people who never look at stars would notice that something fundamental had changed. Depending on how luminous the explosion is, Betelgeuse might even be visible in daylight, a pale, brilliant point against the blue sky if you know where to look. Over months, it would fade as the debris expands and cools, but telescopes would track it for years and decades, watching a supernova remnant form, a growing bubble of gas and dust enriched with heavy elements, spreading into the interstellar medium. For astronomers, it would be the best observed nearby supernova in human history. We'd study its spectrum, its light curve, its neutrinos, and possibly even gravitational waves. For everyone else, it would be a once-in-many-generations sky event. The only frustrating part is that we don't know whether this happens in our lifetime or thousands of years from now. And that uncertainty is why every strange change in Betelgeuse gets people's attention, especially what happened in 2019. The Great Dimming was it. In late 2019, astronomers noticed something odd. Betelgeuse, which normally fluctuates a bit, was fatting more than usual, a lot more. Over the next few months, its brightness dropped to about 40% of its normal level. Orion looked wrong. The bright shoulder of the hunter seemed to shrink. Speculation exploded. Was this the warning sign? Was Betelgeuse about to collapse? It's not an unreasonable thought. Some models suggest that massive stars could become more unstable in their final years or decades. But what those final warning signs would look like isn't clear. Headlines made it sound like Betelgeuse might blow any day. Then better observations arrived, and the story changed. High-resolution imaging showed the dimming wasn't uniform across the star's face. One side was affected more than the other. Spectra showed changes consistent with material being thrown off the star. The leading explanation now is surprisingly physical and simple. Betelgeuse likely had a major surface eruption. A large amount of hot gas was blasted outward. As that gas expanded, it cooled. As it cooled, it condensed into dust. And from Earth, that dust acted like a moving veil. A clump of it drifted across part of Betelgeuse's face and blocked some of its light. The star didn't necessarily turn off. We were looking at it through its own debris. By mid-2020, the dust dispersed and Betelgeuse brightened again. The Great Dimming ended. That taught us two things. First, Betelgeuse is more active on short timescales than we fully appreciated. It can eject huge amounts of material and change its appearance for months. Second, dramatic dimming does not automatically mean supernova tomorrow. Red supergiants have other ways to look alarming. But the Great Dimming also did something else. It triggered a wave of new observations. And those observations helped push forward two of the biggest remaining mysteries: whether Betelgeuse has a hidden companion and why its rotation looks so strangely fast. Does Betelgeuse have a hidden companion? Massive stars often don't live alone. Many form in binary systems, orbiting partners and sometimes exchanging mass. For decades, astronomers have suspected Betelgeuse might have a smaller companion star bound to it by gravity. The clues are subtle, but they add up. One clue is its complex brightness cycles. Betelgeuse doesn't have one clean pulse. It has several overlapping rhythms, some hundreds of days long, others stretching over years. One especially long cycle, close to 6 years, is hard to explain as simple internal pulsation. Some researchers have modeled that slow cycle as orbital, a smaller star circling Betelgeuse, tugging on its extended atmosphere, or adding a tiny amount of extra light that changes as the orbit progresses. Another clue comes from precision measurements of Betelgeuse's motion across the sky. Instead of drifting perfectly smoothly, it shows a slight periodic wobble, as if something unseen is pulling it. Combine that with subtle shifts in spectral lines, and you can model Betelgeuse as moving around a shared center of mass with another object. And in the last few years, high-resolution imaging has produced tentative hints of a faint point of light close to Betelgeuse, at times consistent with the predicted orbit. These detections are difficult and not yet definitive, but they're intriguing. If the companion exists, the best guess is that it's a relatively normal star, perhaps comparable to the Sun, orbiting at a distance similar to the Sun-to-Saturn range, taking several years to complete an orbit. If that picture is correct, it changes the story in three ways. It could explain at least one of Betelgeuse's long brightness cycles. It could help explain aspects of Betelgeuse's past evolution, including how it lost mass and how it retained or gained angular momentum. And when Betelgeuse finally explodes, that companion will be inside the blast environment and will be hit with radiation and debris, an astronomical drama playing out in real time, 650 light-years away. But even that is Betelgeuse's strangest puzzle. The most mind-bending mystery is its rotation. The rotation mystery, fast spin or optical trick. Because Betelgeuse is huge but distant, we can only barely resolve its surface, even with our best instruments. We can't simply watch a spot move across it the way we can with the Sun. So astronomers use the Doppler effect. You've heard it in sound. An ambulance siren sounds higher as it approaches and lower as it moves away. Light does the same thing. If something moves toward us, its light shifts slightly bluer. If it moves away, it shifts slightly redder. For a rotating star, one side should be slightly blue shifted and the opposite side slightly red shifted. Measure that difference and you can estimate rotation. Using powerful millimeter wave radio observations, astronomers mapped Betelgeuse and found a subtle gradient across the star, one side slightly blue shifted, the other slightly red shifted. The simplest interpretation is rotation. When they translated that gradient into a speed, the result was about 5 kilometers per second at the surface, implying a rotation period on the order of decades. And that's where the problem appears. For a star as bloated as Betelgeuse, theory says the surface should be rotating extremely slowly. As stars expand into red supergiants, their rotation should slow dramatically. On top of that, massive stars lose angular momentum through winds over time. By this late stage, a fast surface spin is not what we expect. So how can Betelgeuse look like it's spinning so quickly? One possible explanation is an extreme past event, a merger or a close interaction that dumped extra angular momentum into Betelgeuse, spinning it up. Stellar cannibalism can do that. But there's another explanation that's almost more interesting because it doesn't require a dramatic backstory. It comes from Betelgeuse's surface itself. Those giant convection cells, the boiling patches of rising and sinking gas, move at significant speeds. Some flows may reach tens of kilometers per second. Each bright upwelling can create a local blue shift or red shift depending on how it moves relative to us. If we had perfect resolution, we'd see a chaotic mosaic of blues and reds across the surface. But we don't. Our instruments blur Betelgeuse into only a limited number of resolution elements. When you blur a chaotic mosaic, sometimes it can accidentally resemble a smooth gradient, exactly the kind of clean pattern you normally interpret as rotation. Researchers have tested this directly. They took realistic simulations of Betelgeuse's turbulent surface, observed them with virtual telescopes that mimic our real resolution limits, and then analyzed the data. The result is surprising. In many simulations, turbulence plus blur produces a rotation-like signal, even when the underlying surface is not rotating nearly as fast as the measurement suggests. In other words, part of Betelgeuse's impossible spin might be an illusion. To settle it, astronomers need sharper data, higher resolution imaging at multiple wavelengths, taken repeatedly over time. If the red-blue gradient stays aligned in a stable direction, that supports real rotation. If the direction wanders and changes as convection patterns evolve, turbulence is likely fooling us. Either way, Betelgeuse is forcing us to improve our methods, because it's a rare case where we're trying to measure rotation on a star we can barely resolve. A star on the edge, but not our doom. So where does all of this leave us? Betelgeuse is a massive, evolved red supergiant nearing the end of its life. It's unstable, turbulent, and leaky, throwing off gas and dust in enormous outbursts. Sometime in the near astronomical future, whether that's 100,000 years from now, 10,000 years, or unexpectedly sooner, its core will run out of fuel. Gravity will overwhelm pressure, the core will collapse, and Betelgeuse will explode as a core collapse supernova. When that happens, Earth will be safe. We're far outside its likely danger zone. Our atmosphere will survive. Our magnetic field and the sun's heliosphere will help shield us from much of the incoming particle storm. From our point of view, Betelgeuse's death will be a sky show and a scientific treasure, not a doomsday event. Until then, Betelgeuse will keep doing what it does best, confusing us. It will brighten and dim in ways that don't always make immediate sense. It may reveal more about its possible companion as we sharpen our imaging. New measurements will refine our estimates of its mass, radius, and true spin. And every twist will teach us more about how massive stars live, die, and seed the universe with the elements that later become planets and life. If nothing else, Betelgeuse is a reminder that the fixed stars above us are anything but fixed. They are living, changing objects, each with its own story and fate. So here's my question for you. Which explanation do you think is more likely? Is Betelgeuse truly spinning fast because of a dramatic interaction in its past? Or are we mostly being fooled by an optical illusion created by its boiling, turbulent surface? Comment spin or illusion and tell me what convinced you. And if you enjoy deep dives into strange stars and cosmic mysteries, consider subscribing to Celesti Logic. Whenever Betelgeuse does something new, or the next weird object shows up in our sky, you'll be the first to know.